So welcome. Many of you I recognize from last week. Some of you I recognize from Solano Community College, so thank you for coming. And this is a topic that we're all interested in, sustainability. Without sustainability, our community, well, as a teacher I always say don't use a word in its definition, but without it, we're not sustainable. And in order to have a discussion like this, there's usually some triggering mechanism that makes people start to discuss a topic. And in the case of sustainability, a lot of what triggers the discussion or triggers people's interest is climate change. So last week we talked about sustainability in general terms, its social components, its economic components, and its environmental components. Tonight we're going to focus on the climate change aspect. And I love living in a world of satellites. For those of you who don't know me, I'm a geologist by training. And so for me to be able to see the world from space, I always thought when I was in college that I was going to be the first woman in space. Sally Ride beat me to it, and then I gave up and decided to just stay home and study it from here. But satellite images give us such a great perspective that I had to start with one, although this is, of course, a false color image showing the temperatures. Oh, and I put a website at the bottom because any of the figures in this PowerPoint presentation that don't have a reference are from this EPA website. Most of them come from the National Oceanic and Atmospheric Administration. But so anytime you don't see a citation, it came from this. And I would really recommend that any of you who are interested in it go to this website. They have a very good set of information on all different aspects of this and the best graphs. And as a scientist, of course, I want graphs. Climate change is nothing new. I'm a geologist. To me, any sense of time without the word millions of years after it is meaningless. So to me, time is measured in preferably hundreds of millions of years. So I needed to start with the geologist's perspective of climate change. And climate really is more than just temperature. So when we talk about climate, what else are you thinking about? There's temperature. Yeah, so rain or precipitation, wind patterns, things like this. But I'm going to talk a little bit about those, but I will focus on temperature. It's one of the easiest ones to measure from the past. And so this chart shows us temperature change over time. Now, time, MA, for those of you who are not in the know, means millions of years ago. When I was in school, they used MY for million years. Now it's MA. Okay. Notice the time scale on here. For one thing, it's not linear. But 570 million years to the present. So I'm taking the long view here. But that blue line is the temperature curve. The red line is the average over about this time period. Notice where we are today. Well below average. Okay, so who got that right on your quiz? See, you thought the quiz was just for fun. Accountability here. We are well below average. We are still, in a geologist's perspective, in an ice age. We're in an interstitial period. We're between really cold ice age periods, but we are still technically in this sort of long ice age period.
So the low temperature on the right?
Yes. Right, so it's cold on the right and warm on the left. I don't know if I can get my finger to show it, but that warm period right there, can you see where the shadow of my finger is? That's the dinosaur period. Okay, it was much warmer when the dinosaurs were on the planet. This really cold blip here is the biggest mass extinction in Earth's history. We always think of the dinosaurs as being the big one, but they're not. They were the sexy one. This was one of the biggest. The other really big one was this cold period. So these are the two biggest extinctions. And then the dinosaur one was not really so climate related.
So where does the Ice Age come in there?
Well, the Ice Age has been a whole period, but basically right about in there. That last little blip. And if you were to look at this in a more detailed version, it would have a sawtooth pattern because we've had, depending on where you are on Earth, 5 or 6 different glaciers advance, retreat. You go to Yosemite and you go look at the signs and they'll show you like 5 or 6 different periods of glacial advance and retreat. So it's been the last few million years.
Well, the Ice Age was about 10,000 years ago.
The last one ended about 12 to 15,000 years ago. Right, but they started, the first one in this sequence started, depending on where you are again, but somewhere between 2 and 5 million. Okay. So that's first thing that is something that most people don't realize. We talk about global warming. The Earth is getting hot. We need to panic. Let's save the planet. Wrong. The planet is fine. The planet's going to continue to be fine. What we're fighting for is to save human civilization. Okay? The planet has been much warmer than this in the past. It will be warmer than this in the future. The cockroaches have survived many of these blips in the past. They will outlast us. So really, when people talk about saving the planet, in my opinion, they're defining the problem incorrectly. What we are fighting for is to save human civilization and human culture as we know it, because our cultures, our way of life is developed in this relatively stable, cool period. Okay. So first thing is I would say rephrase your question. And to me, that's actually reassuring. I don't know. When I first started thinking about this, I thought, we're messing up. I mean, we are messing up the planet. I'm not saying this is good for the planet. Don't get me wrong. Okay. So I am not at all saying that some of the changes are good for the planet. But to put it in perspective, I really think the Earth is going to be okay. And climate change, as you saw, was happening long before humans got here. There are lots of natural causes of climate change. Milankovitch cycles. Okay, who knows this one? What did you say? It's the variations in the Earth's orbit. There's actually 3 different cycles, a 100,000-year cycle, a 41,000-year cycle, a 12-year cycle. You will not be tested on that. They have to do with, the fact that when the Earth goes around the sun, it's not really a circle, it's an ellipse. And sometimes it becomes more cigar-shaped and sometimes more circular. And that if it's more cigar-shaped, then you have more extreme climates. The angle of the Earth changes, and that can influence the severity of the seasons. So these natural variations play a major role in ice ages and climate change.
It was 100,000 and then what was
41,000, and then around 11 or 12,000. Another big variation is energy from the sun, right? Solar energy output is not constant. This one can cause it to warm up or cool down. If there's more solar flares, we tend to get more energy. If there's more sunspots, we tend to get less. So it can go either way. Lots of historians have tried to relate some of the medieval warming period to an increase in energy put out by the sun. So that's another variation. Volcanoes, No geologist can have a talk about anything without discussing volcanoes, right? And again, see, that was the sound of a volcano erupting. That was in my class. But volcanoes can either warm it up or cool it down. They put out sulfur dioxide emissions, which actually reflect sunlight back and can cool, opposite. The sulfur dioxide absorbs the energy and makes it warmer, but it can put out ash and other aerosols which can blanket the sun, make it cooler. Tambora volcano from Indonesia, when it erupted, and I wrote down the date and then forgot to bring it with me, 1860 something, we'll say it with conviction and nobody will tell me I'm wrong. It's what caused the year without summer, caused global temperatures to drop by about 5 degrees for a couple of years. Apparently, it made the world so dark that in London, which is halfway around the world from Indonesia, for those of you who are geographically challenged, used headlights, which were lanterns in 1860s, at midday. It was so dark that it was like dusk and they had to use lanterns at midday. So there are lots, and so the people who try to say that we shouldn't worry about climate change, this is usually the arsenal of information that they use. They say climate change is natural, it's happened before, it'll happen again, and they're absolutely right. It has, and again, like I've said, the earth will be fine. The catch is humans haven't been here before for some of the variations that we're talking about. And we're human, so we care more about us than the dinosaurs or the corals or things like that. So the next question is, how are we affecting climate? Because we are. On a very local level, I don't know how many of you have heard that term, urban heat island. Right. Large cities, they've been able to document that in and around large cities are 2 to 5 degrees warmer than the surrounding countryside.
Are you talking Fahrenheit or?
That's Fahrenheit. 2 to 5 degrees Fahrenheit. And you do need to check me, because usually if I'm talking modern day, I use Fahrenheit. When I go back in time, I usually go Celsius, so you do have to check me, so thank you. And this changing in temperature around cities actually changes precipitation patterns. They've been able to document around Houston, Texas, that the afternoon rainstorms in the summer afternoons have changed their pattern and intensity based on this. It also changes the direction of wind pattern. Because the wind tends to blow in from the country when you have an urban heat island, which sounds great. Bring that fresh country air into your town. But what do they usually build on the edge of town, between town and country? Factories. Of course, malls, strip malls, but that doesn't matter. It's the factories. So most of the manufacturing. So then they do that to get the pollutants out of town, but then the urban heat island causes the wind to come in and bring all that pollution into town. But that's a pretty localized fact. Deforestation. Have any of y'all been to the Amazon? Which part did you go to? Okay, so that's what I was hoping you'd say. It was either Ecuador or Peru, but up in the Andes in like the Rio Napo or that end. Okay. The forests there are dying. The forests on the Andes are being hit hard by climate change. They're one of the most hard-hit parts of the world. The forests on the east side are dying because they used to get their rain, comes from, let me figure out which way you're looking, South America, Atlantic Ocean. The wind would come from the Atlantic Ocean, blow across the flat country of Brazil, and then as it would go up the mountain range, it would start to rain. It would rain all in through there. But it would get about halfway across Brazil and it would have lost its moisture, right? Because it's been raining for a few hundred miles. But trees take the moisture out of the ground and breathe it out through their leaves, or transpire it, out through their leaves. So it's losing moisture through rain, but picking it up from the trees so it can take the rain further inland, where it drops more rain but picks up more moisture from the trees, drops some rain, pick up moisture from the trees, and keep going. Take away the trees, and that rain just soaks into the ground, and there's no replenishment of the clouds. So the forest is shrinking down the Andes because the rain is no longer making it as far over. So whenever we think about deforestation, we tend to think about clear cutting and the blight on the landscape and not getting the carbon dioxide and stuff like that, but it's actually causing the destruction of the forest on the, or the shrinking, I shouldn't say destruction, but the shrinking of the forest in that area. So, issues. But the one that we're, of course, most global concern, because we don't live on the flanks of the Andes, are the greenhouse gases. So when a lot of people think of climate change, global warming, and greenhouse effect as the same, they're not. Each of them is different. Climate change is just what the name implies. Changes and variations in the climate. Colder, warmer, now, back with the dinosaurs. Who cares? The climate varies. Okay. Global warming. Again, aptly named. The planet is getting warmer. Doesn't imply causation. It's just a statement of fact. We can measure the fact that the planet is getting warmer. Period. Fact. Then you start talking about why is the planet getting warmer. And that's where the greenhouse effect comes in. Okay. So I've got another question. It's not on your quiz. How many of you think of the greenhouse effect as a bad thing? Okay, it took a few bold people to get that, because it gets a bad rap. But I'll tell you, the greenhouse effect, you're glad we have the greenhouse effect. The greenhouse effect is like chocolate. Life without it is not worth living. Okay? But it should be taken in moderation. And that's our problem now with the greenhouse effect, is not that we have one, but that it's sort of gone wild. So it's greenhouse effect gone wild that's the problem. There are estimates, and depending on who you ask and what model you looked at, you'll get different numbers. But usually, most scientists will say that without the greenhouse effect, the natural background level of greenhouse gases, our planet would be about 60 degrees Fahrenheit colder than it is now. Okay. The high temperature, this was a lovely day. Don't you think it was a lovely day? What was the high temperature today? 70? 63. Okay. That means if without the greenhouse effect, it would have been 3. Right? Think about how many days we have. It would have to be over 92, right? 92 minus 60 gets you to freezing. So without the greenhouse effect, only days we would get over freezing would be the days that currently go over 92 degrees. And in much of the world, that would mean that it would just be frozen all the time. So the greenhouse effect is not inherently bad. It's like chocolate. You know, if you eat nothing but chocolate, it's bad. But eating some chocolate is very therapeutic. Right. Trust me, I run this experiment several times a week, and it always works. Okay. So, the greenhouse effect takes place in our atmosphere. When we talk about the greenhouse effect, we're talking really about warming of the atmosphere and the warming of the air. And before I can talk really about this, I brought my globe. Did I mention I'm a geologist? Geologists never go anywhere without a globe. Okay, let me find my other prop here for just a second. I had another prop. It's okay, I brought a spare. Okay. So here's the Earth. Oh, there's my prop. I want you to look at the Earth and visualize the atmosphere. Okay, and I admit there's no sharp outer limit to the atmosphere. It fades away. So for those of you who are really picky, when I say the atmosphere, I'm talking about the troposphere and the stratosphere. And so this will contain about 95% of the mass in the atmosphere. So the top of the stratosphere. Okay. And I'm going to bring my finger in. I hope I'm a place where you can all see me. I'm going to bring my finger down, and I want you to raise your hand when you think I've hit the outside of the atmosphere. I'll tell you it's not this thick. Okay. Okay, I've got a hand. One bold person. Okay, a couple of bold people. More bold people. Okay, oh, lots of movement. Yeah, oh, look at the hands flying, flying, oh. And this fact scares me. Do y'all recognize this? Do any of y'all have small children? Fruit roll-up. Fruit roll-up. There it is. That's something to lose sleep over. All that stands between us and the abyss of outer space is one fruit roll-up. I mean, how do we sleep at night? But I mean, seriously, this is it. When we talk about the atmosphere, most of us think of this big protective buffer zone. And so if we mess around with the part right here near the surface, who cares? We've got all the rest of that out there to dilute it, right? That's it. So we need to take care of our fruit roll-up, because we mess this up. There's not a lot of leeway there. And if anybody wants to see the math, I will do it for you. In my classes, I always make them do the calculations, but I'm not going to make you do that. And it's about 1 millimeter thick, in case you're trying to do it. And I think the Earth is about 15 centimeters in radius, for those of you who want to test your own algebra skills. Okay, so important point. The atmosphere is very thin and very delicate. And it's warming up. So most of you have seen some variation of this slide. It comes in all different forms. But this is just showing the temperature from 1900 to 2010. Average temperature across the middle. The blue lines were years that were colder than average. Red lines are years that were warmer than average. So don't look at this. I should have asked the question before I did this. How many of the warmest 10 years on record have occurred since 1990? All 10. And this always shocks my college students, because I never phrase it this way. I say, how many of the 10 hottest years on record have been in your lifetime? And all 10 of the hottest years on record have been in the lifetime of my college students. Because if they thought it was in my lifetime, she's so old, that's like ancient history. But their lifetime is short, and they've seen all 10 of the hottest years on record. And I could not find the number for 2010, but as of September of 2010, which was the last data I could find, it was tying for first. So we've now added another hotter than the hottest. So it is, global warming is fact. Okay. Anybody who wants to argue global warming, you explain to them it's measurable, it's a fact. There's other things we can debate. I'm not saying there's no debate, but the debate is not whether the Earth is getting warmer. It is.
And yet we've had the biggest snows in the Sierra on record.
Right. Not going to be uniform. And what we're going to find is that it changes precipitation patterns. So it changes where the moisture goes. So a lot of what's happening is not the difference in temperature, but the difference in moisture. And if you think about it, the places that get the most slow, let me try again. Let's try it in English. The places that get the most snow are not the coldest places. Okay. Again, for those of you who were here last time, where did I do my dissertation field work? The Brooks Range of Alaska, which is way up north. They get about this much snow a year. And you can tell because there's no trees up there. We're completely north of tree line. But the willow bushes in the valleys were all exactly this tall. It was like somebody came in with a giant weed whacker and leveled all the bushes at the same height. Because it gets so cold there in the winter that anything that sticks out of the snow freezes off and dies. So the snow is actually the insulator. So you could tell exactly how deep the snow had been in the valley because that was the height of all the willow bushes, which is nice because moose and grizzly bears are taller than the willow bushes, which is nice. Okay. Now, I lived in Tahoe for 7 years. That was like one snowstorm. That's the annual. So temperature is not the key. It's the combination of temperature and moisture at the right time in the right place. So yeah, people are going to try that line on you too. Don't fall for it. Okay. So it is getting warmer. Oops. And carbon dioxide. And this, when we talk about greenhouse gases, we focus on carbon dioxide. It's the most voluminous. It's the most prevalent. It's the one we generate. It's the one we've been measuring for the longest. There are others, such as methane, nitrogen oxides, water vapor. Good guess. Wasn't that tricky? Right? All of those things you don't think about. Everybody expects carbon dioxide, so I didn't include that. Okay. But yeah, water vapor, that's a greenhouse gas. Right? We don't really influence it very much. But notice the change. Right? Carbon dioxide's changed over the past. Notice this one is not quite geologic time, but we're still talking hundreds of thousands of years here. They get this data mostly from cores and glaciers. Because they can actually, there's actually little bubbles of atmosphere trapped in there, and they can also go into the oxygen atoms and look at the isotope or the weight of the oxygen, heavy oxygen, light oxygen. I actually had a graduate student, and this guy was smart. He did his dissertation work studying stalactites in caves in Jamaica. Now that's a good gig. But what they were doing is stalactites, cave formations, are made of calcium carbonate, which has oxygen. And the rings, I don't know if you're aware that they actually have rings like tree rings. And they could go back and date the different layers and see how the oxygen had changed over time in these stalactites because they were looking for it in how it affected the tropics, not just the glacial areas. So, and then there is the one that to me is just so convincing. That's showing temperature and carbon dioxide concentrations superimposed. And my sister, the statistician, always tells me that correlation is not the same as causation. But I'm telling you, even she would have a hard time saying that there's not a cause and effect in that perfect degree of correlation.
That's particularly Antarctic.
This is Antarctic temperatures, but this was just the graph that I could find that showed it really well. If you do global mean temperatures, it shows as well. I had another one where it had about 6 different sets of temperatures, but the slide got so messy that it didn't show. So it works on any way that you measure it. So carbon dioxide is the main greenhouse gas. Nitrogen oxide is more powerful, but there's not much of it. It absorbs like 300 times as much energy, but there's so much less of it that its effect is smaller. So now the question is, and I can't remember what I put next. Oh, here we go. How does the greenhouse gases warm the atmosphere? And this is something that's a little weird, and I find it fascinating. That the temperature is controlled by the Earth's heat budget. Yeah. We all know about budgets. What comes in, if it equals what goes out, everything stays the same, just like your checkbook, for those of you who remember checkbooks. But your bank account, right? If the in and the out are equal, then the balance stays the same. And that's true with the Earth's surface. If the energy in from the sun, wait, don't look at that. If the energy in from the sun is equal to the energy that the Earth loses out to space, then the temperature stays pretty constant. So if we either get more energy in from the sun or lose more energy out to space or vice versa, any of that, it can make it get colder, hotter, what have you. And notice that I have this in and the out in different colors. And this is the crux of the matter, that the energy in from the sun, the energy we get from the sun, is fundamentally different from the energy that the Earth puts back out into space. And this is all electromagnetic radiation, and it's physics, and it's really cool. You're getting the short version. Hot objects like the sun send out very high energy. Think of them as kindergartners, bobbing up and down. They're small and fast, right? Kindergartners are small and fast, bobbing up and down really fast, really small little waves, really fast and easily distracted, okay? Whereas cooler objects, lower energy objects, like me, I'm cool. I'm a little more slow-moving than the average kindergartner and a little larger. That's what the Earth's energy is like, too, because the Earth is cooler than the sun. Okay, so cooler, and you are putting out energy right now. Everything puts out energy. The amount of energy it puts out, and whether it's long wavelength or short wavelength, high energy or low energy, that varies. But that chair is putting out energy right now. We don't see it. This light bulb is putting out energy. We see it as light. But everything does, but different kinds. So, but the two things we care about are the Earth and the sun. So the sun puts out high energy, short wavelength, ultraviolet, and visible. Right, so you can see the different kinds of rays there, X-rays, ultraviolet, visible. Obviously, it puts out visible light. We see it, but also lots of ultraviolet and a little bit of infrared and other things, but mostly ultraviolet and visible. Whereas the Earth does not glow, right? So it's not visible. It's in the longer, lower energy wavelengths, the infrared. Who got that one right? Right? That's I'm sorry. I didn't ask that question, did I? I'm getting ahead of myself.
The inverse of that question.
Oh, what did I ask?
What are absorbed by?
Oh, okay. So here's the thing. Kindergartners go right through the atmosphere. The short wavelength, high energy, ultraviolet light of the sun mostly just goes right straight through. The really short wavelengths of visible light bounce off to the side. That's the blues. This is why the sky's blue, right? Is because the short wavelengths sort of bounce in all directions. So you see them, whereas the longer wavelengths go straight through and the sun looks sort of yellow or red. Right? But that's a different lecture. Take meteorology and I'll explain it.
Is that why you still get a sunburn on a cloudy day?
Yes, because the waves are still there. They're just sort of coming from more directions. You usually don't, with me, I burn, okay? Let's just face it. On a sunny day, I tend to get a real sharp line where the sun hits and doesn't. On a cloudy day, it's less of, because I'll get a sharp line here where the sun doesn't hit.
Shorter wavelength ultraviolet, which causes the burn, will come through the clouds.
Right. Well, because clouds are greenhouse gases which absorb the infrared. Right? So they block that part of the sun, but still let the UV in. So sunlight comes through the atmosphere, hits the earth takes it all in. The earth is close to being a black body, which means it absorbs all the energy that comes its way. It absorbs that energy, it takes it in, uses it as its own for the most part, and then re-emits the energy in a different form. And that different form is the infrared. And that's what's getting absorbed by the greenhouse gases. So the same amount of sunlight comes in, but less of the Earth's heat gets back out, right? Because the Earth has changed that sunlight. Because if the Earth didn't change the sunlight, what comes in could go right back out, and there would be no greenhouse effect. It's that transformation from short wavelength ultraviolet to long wavelength infrared that makes it into the energy that gets absorbed. Again, good thing in moderation. It's just, so that first 60 degrees or so of greenhouse effect is good, but we as a civilization and a people are adapted to that level. And if we suddenly get an extra 5 degrees or 10 degrees, that's going to be the problem. Oh, yeah, I already said that. So here's the graph showing various estimates of what's going to happen with the carbon dioxide in the atmosphere. So it goes from 1900 to 2000, and then I think they used, I can't remember now whether it was 2000 or 2010 as the branch off point. If we stopped completely adding carbon dioxide to the atmosphere today, temperature is still going to keep rising a little bit. So you'll notice that even the fairly flat curve, the yellow one, that one, that's if no carbon dioxide, if we stop burning all fossil, because let's face it, the main way that we're putting greenhouse gases into the atmosphere is by burning fossil fuels. And fossil fuels are anything that were once alive. We always think oil, gas, coal, but this is also wood, cigarettes, charcoal, forest fires, anything that was once alive, that's the pile of leaves in your backyard, anything that was once alive, that steak on your barbecue, is producing this. And then you can see the other levels of low growth, moderate growth, and high growth, just depending on how much we can rein in our consumption of fossil fuels. Some of the other greenhouse gases like methane have other sources. They're partly related to this. Rice farming, however, can be, depending on how it's done, a fairly large source of methane. Because it can be produced by certain bacteria and stuff in the rice paddies. So depending on what technique is used for rice farming, that can do it. And then, of course, there's the flatulent cow model. But this diagram to me is fairly telling. It's showing at the top the low growth model, and then the middle, moderate growth, at the bottom, high growth. That's those different curves, how much carbon dioxide we put out into the atmosphere. On the left is up until 2029. That's just how much change we can expect to see in the next 17 years, the next generation of college students coming around the block. And then on the right, it goes up and jumps up to 2090, 2099. And that's the amount of change. And you'll notice that these temperatures are in Celsius, Celsius. I can never remember. They stopped using centigrade and they went to Celsius. And so you can see that some of those, and for those of you who don't do Celsius, 1.8 times Fahrenheit. So that 8 degrees of Celsius, which is the high amount, is about 14 or so degrees Fahrenheit. So that's a lot. I mean, think if today had been 14 degrees cooler and it had been 50 degrees, we would not have been thinking it was such a nice day. But now take a look at that and you will see that there are variations. Not everywhere is getting a whole lot hotter or a whole lot cooler, but notice that the Arctic, that the polar regions are affected the most. A lot of this is because ice does not absorb sunlight. The sunlight, when it hits the ice, instead of being absorbed and changed into ultraviolet, which heats up the atmosphere, it bounces right back into space unchanged and then will whiz right back through the atmosphere as ultraviolet. So as we start to lose the ice in the Arctic, less of the sunlight bounces back into space, more of it goes through that recycling into infrared process and heats the atmosphere. So it's one of these horrible feedback loops.
So that's ice. What about liquid water? Does it absorb?
Water does absorb it. Yes.
So that speeds up.
Right. But water has, and of course it depends, and it can also depend on just how choppy the water is. If water is really smooth, then it can be fairly reflective, but even a small amount of wave or chop on the surface tends to make it absorb. But water is very good at holding energy too, so it does not send it back as readily. It stores more of it in the water rather than heating the atmosphere near it, which, thank you, is a nice segue into the second point, which is you'll notice that the continents are more affected than the oceans, partly because the oceans are actually holding more of that energy in the water, whereas land is not as good at holding it and puts more of it, re-emits more of it. So the polar regions are more affected, the land regions are more affected.
Why does it look like Greenland gets spared?
Isn't that cool? Okay, I was going to do this later, but I can't resist. Okay, which place on Earth is likely to have the least? I had struggled with the wording on this. Which place doesn't get as hot as anywhere else? You said Greenland. I put down Ireland, because that cold spot actually sort of hits much of Great Britain. There are actually, in some models, they say that Britain might actually go into another little ice age as a result of global warming. With everybody else heating. And so, but look at that spot. And I've got another map later that shows it even better because the colors are better. And so this is weird. You're going, now, wait a minute. This is a result of the Gulf Stream. How many of you have been to like London or somewhere like that? Okay. Did any of you go in the winter? How cold was it? No, it was miserable. It was miserable, but it wasn't freezing, probably.
Was it November?
Really?
No.
Oh, okay, because usually in London they don't. Okay, so I'm not going to listen to her. When were you there?
I was in Ireland, and it was like the most snow they've had in years.
Well, thanks a lot. You were there. Usually in that part of the world, thank you to the rest of you, it's usually cold and gray and drizzly and miserable and awful, but usually not particularly snowy and cold. But take a look at this latitude. And this is something most of us don't realize because it seems so wrong. Okay, so follow my shadow. There's London. Let's go straight over. That's like Canada. That's southern Alaska. We think of London as being at maybe the same latitude as, Philadelphia or New York, right? Because it's sort of that weather. It gets cold and it snows sometimes, but not that much. No, New York is down here. London is way up there at much closer to the latitude of Anchorage, Alaska. But it's way warmer than it ought to be. I mean, we think of Spain. Don't you think of Spain as being sunny and warm and tropical almost? Madrid is at the same latitude as like Boston. I don't think of Spain and Boston in the same thought, except with a negative in between them. But that part is much warmer than it normally would be. Here, let me use my glow. I can reach it. Okay. They're stealing from us. They're getting back at us from that whole tea thing a couple of hundred years ago. What they're doing is they're stealing the warm water from the Caribbean. Ocean currents in the northern hemisphere travel clockwise. So look at that warm water from the Caribbean, comes up along the east coast, along to about North Carolina, somewhere about there, and then starts shooting over until it bumps into Ireland or Spain. So warm Caribbean water goes right over and bumps into that part of Europe. The thought is, as the glaciers start melting in Greenland, that the cold surface water from Greenland is going to melt and go down on the surface because it will be fresh water. Glaciers are fresh water. Fresh water floats on salt water. So that cold water is going to come down on the surface and push the Gulf Stream south. And so sooner or later, instead of coming up from the Caribbean along the coast into Western Europe, it's just going to come down and hit the coast of Africa. So that warm water is going to be hitting Morocco or something instead of Ireland. How many of y'all got that one right? All right, okay, good.
Sure it's all going south? I'm asking the question. Sure it's all going south? Because I know that a lot of it's going deep.
Right. There's this whole conveyor that some of it is going deep. But it's getting off of the surface. Yeah. And but he is right. I'm doing it in a very two-dimensional way, and it's this whole conveyor belt that goes down deep as well. We, of course, I'm sorry, I'm a meteorologist too, can't be helped. We're on the downside of a loop, the Pacific Gyre or loop. Where's our water coming from? Alaska. Have any of you touched the water? I'm from Texas. Water is not supposed to feel like this. Just letting you know. Okay. So the greenhouse effect is causing this warming. Good thing in moderation, too much of a good thing. Some of the probable impacts that we're going to have, and I've already mentioned some of these. Melting of glaciers and sea ice. The Andes, again, are going to be hit hard. And when were you in Peru?
4 years ago.
Okay, so they were already feeling the effects by 4 years ago. I was there about the same time. We may have seen you there. But there are villages in the high Andes that have already had to basically be abandoned because the glaciers up there in their mountains, this is actually in Ecuador, that's Cotopaxi. I actually took a class up and we touched that glacier at 16,000 feet on the equator. That was a fun trip. But they're losing it faster because they're no longer getting the snow replenishing it. So their whole agriculture was based on getting the water from the melting glaciers during the dry season. It would replenish during the wet season, and that cycle went. Now, in the wet season, it rains instead of snows. It's melting faster, and so their whole agriculture-based economy is just shot. It's happening. You can practically watch it happen. Okay.
It's true in the Himalayas.
The Himalayas is,
Pakistan
and
China.
right. It's happening a little less dramatically because there you have the whole mountain range. It's a little further north. It's a little higher. So here it's isolated spots. So when that isolated spot goes, it's gone. So it's the same thing, but just a little bit less dramatically. I went to the Columbia Glacier in 1984, driving up to Alaska, one of those summers to do my field work, and took my picture at the foot of the Columbia Glacier. My husband and I went back about 2 or 3 years ago. That glacier had retreated over a half a mile. And I was trying to see if I could find the pictures from before and after of me standing there with the glacier. In New Zealand, I went and hiked up to this glacier, and I climbed up the little observation platform that was built so that you could like reach out and touch the glacier. The glacier was a mile up the valley. You couldn't even see it anymore. The platform had been built in the 70s. Couldn't even, you could just sort of see a hint of glacier up there. And then sea ice. The Northwest Passage was ice-free for the first time since satellite pictures have been taken of it. And I think it was last year was the first time. So we've all seen the pictures of the polar bears swimming around. They're going to be doing more swimming and less sitting. One thing you may not think about, garden people, changing in plant hardiness zones. Agriculture is going to have to shift. If you used to grow rye, now you're going to grow wheat. If you used to grow wheat, now you're going to grow corn. If you used to grow corn, now you've got squash and beans. After that, you're moving north to where you can grow something else, okay? So the length of the growing season, I found that pretty amazing. Look at the number of days. So just since 1970, the growing season has lengthened by about 12 to 15 days. That's significant. Fewer freezing days. So those of you who have fruit trees that need a certain number of freezing hours or things for the fruit, you went and chose the species that works in your climate. Sorry. Lovely flowers, no fruit. And then the plant hardiness zones. The acidity of the ocean is going to increase because carbon dioxide dissolves in water. If you ever drink a soda and it feels fizzy on your tongue, that's carbonic acid. That's just carbon dioxide dissolved in a liquid. It's acidic. Not good for coral, not good for plankton, not good for delicate sea life, not good for all sorts of things.
I think you also mentioned the aspect of coral, and that 80% of the fish species variation is associated with coral reefs, and that the loss of coral is really the loss of species.
Absolutely, absolutely. And they're finding that entire coral reefs are practically disappearing or getting bleached out and dying. I say overnight, but again, to me, if it doesn't have millions of years attached, it is overnight. But I mean, I'm even talking in a fast for human, in a matter of a couple of years. Changes in precipitation, increased hurricane intensity. So how many of, didn't I ask that question, of the most intense hurricane seasons have been, since 1990 have been, whatever, how many? Nope. Nope. 6. I thought I'd trick you with that other one that went extreme. But still, 60% of the most extreme hurricane seasons have been in the last 22 years. And they've been keeping records since like the early mid-1800s. That's still really disproportionate. Okay. So this map shows some of the anticipated changes in precipitation, and I can tell I'm talking too much, so I'm going to have to hurry. But you'll notice that some places are going to get wetter. Indonesia, don't they need more rain? They're going to get it. But then other places are going to get much drier. What it's doing is shifting the global pressure zones. Those of you who watch the weather know that low pressure gives you rain, high pressure gives you clear skies. What this is going to be doing, and there are normally strips of low and high pressure in the earth, what it's going to be doing is shifting those boundaries and the size of those zones.
So
blue is more water, brown is drier.
So a lot more water over the sea.
See, this is the same reason why there's going to be more hurricanes. The water is getting warmer, right? Instead of putting all that heat out, it's absorbing a lot of it, so the seawater is going to get hotter, which means it evaporates more, which causes more hurricanes and more rain. So the extra rainfall in the tropical ocean regions is directly correlated to that warmer sea water.
And Australia's looking to get droughts.
Yeah. Oh, yeah, and they're already having some nasty ones. One interesting thing that they have trouble fitting into their model, though, is that as the oceans get warmer and evaporate more and form more clouds, clouds actually cool off the planet because they reflect a lot of the sunlight before it ever gets to the earth. So this is one of those things they have trouble putting into the model. Okay, the oceans were getting warmer, so the oceans get warmer, so it makes more clouds, which make it get cooler. So how much is that going to offset the warming? This is the kind of complexity. This is why, people who want nice, sharp answers. How much are we causing this? How much is it going to change? How much should I worry about this? How much of this is my fault? Because if I know how much of this is my fault, I know how much I have to do to fix it. We can't answer that. We can tell that some of it is our fault. Exactly how much, we can't do. And how much do we have to change to fix it? I would say it's better to do more than less. Wouldn't you rather save human civilization than come really close? Just a thought.
How would the weather patterns be changed by this if the oceans are getting warmer? I read this in a book, thermal expansions.
Well, that is actually part of what's causing sea level rise.
Yeah.
So sea level rise will actually be,
Years by 12, 13 inches.
but different in different places. There's actually, I thought about putting that slide in and didn't think I could explain it in the time I had. But yes, sea level rise is related to the melting of the ice caps, but also from the expansion of the water as it gets warmer. In our area there, and I looked this up. I actually even went out and bought a topo map of Benicia. I was going to draw in the new shoreline when the sea level went up 10 feet, just to see, because, Benicia much of it is at sea level.
We have it in our climate action.
Do you? Okay.
You can do a time check.
Okay, good, because I'm at just about my last thing. So, there's the intensity of the cyclones. Intensity of the cyclones going up. And then this is just the slide that I was planning to talk about Ireland getting colder, because it actually shows it going blue. See, so I was right at the end. Okay, so takeaway message. The earth is going to be fine. The cockroaches will be happy without us. Okay, but, it's really people that we're talking about, because sustainability, cockroaches and the planet don't care about the social aspects, the economic aspects. It's the people that we're really worried about here. And so climate change is a natural phenomenon, and some of the current warming is probably natural. But a lot of it is us. We can't put it all off on nature. A lot of it is clearly related to us. And that's the part we have to try to each make our decision of how much are we going to worry about this and what are we going to do about it. Thank you very much. And now Sharon has discussion for you.